Okay, hello everyone. I hope you can hear me. I'm Alessio Capitanelli. I am the speaker right now, and I'm going to talk to you about the use of ontologies in ROS. So if you don't know what an ontology is, don't worry. We're going to have a short primer right now. And then we're going to see some practical tutorial about this in a short while. So if you have the RDS Studio open, let's have a look at the tutorial I left there for you. So these you can find it also on a repository online. I will maybe share the link later. So if later you want to come and have a look at it, there is written, I'd say, everything we're going to see together today, and not just the instruction, but also the more theoretical aspects of it. Okay, so the presentation is going to be divided in 3 parts, most of it. In the first part, as I said, I will give you a short primer about what is an ontology and how it can help you in robotics, which is this part. And then we're going to see what are the components of the framework I'm going to present you, and then actually get to the presentation, okay, or to the tutorial. All right. Okay, so what is an ontology? I want to start by actually open a software that helps you visualize ontologies, and I think it's just easier to grasp it if you see one under your eyes. So an ontology is a term that comes from the Greek philosophy, and it's the philosophical study of natural being and the basic categories and their relations. So it's something that has to do with artificial intelligence, and let's say that it's a way to describe reality in terms of hierarchical classes, instances of said classes, and properties between objects. And ontologies in computer science are just databases that provide support for this kind of representation of the world. Now, this definition is very, very broad, in the sense that it can include something as simple as C++ data structure or something like that. But we're going to refer here to OWL, the OWL standard. Okay, so ontology is written in OWL. OWL is an XML schema that was developed by the Web3 consortium a few years ago when the semantic web was a buzzword. And yeah, it's just a way to use ontologies in a very smart way. Why? Because so let's open one here. Open. I'm going just to show you one. So SRC, let's get one of those we are going to see today. For example, the global ontology is fine. So why I say it's a smart way to do it? Well, this is a very well-known standard for ontologies, and is one that makes use of description logic, which is a formalism to describe reality in terms of logic statements. All right. So you see that you have this. Now, you can open a OWL file in a text editor and create this just by typing in your favorite text editor, but it's usually very verbose and error prone. So I would suggest you to use a graphical interface like this software. You can find the link in the tutorial, and it's free to use. So shouldn't be a problem. It's very intuitive. As you can see, we have some class of objects that you can create here. And then you can open some new tabs here, like for object properties, and see the list of the object properties defined and the links to objects between each other, and so on. And if you want to go a bit in deep here, there is also a tutorial linked on how to use this software, but I think you can manage it yourself also. It's very easy. So why we want to use it? Well, if you look here, there is a little software called Reasoner. We can select one of the one available, and this Reasoner just go through the ontology and then can infer knowledge that is not explicitly stated in your database. So for example, let's make a simple example, all right? I can even run the reasoner here if you want. Now here there is not much to reason, but what happens is that let's assume we have a class like a fruit, and we define a fruit like the class of all objects that have some seeds, right? Now, if we add a new object that has some seed and we don't say that it's a fruit, the database will automatically categorize it as a fruit in the moment I run a reasoner. So there is some implicit knowledge that is not explicitly stated, but using logic, it can be recovered, okay? And this obviously has a great use in robotics because, for example, you can get some deductions from your data readings, or you can react to some user behavior or something like this. And the second thing that is done is called inconsistency checking. And it means that, let's say again, as before, I had an object which has some seeds, but this time I explicitly state it's not a fruit. So what happens? I have two logical statements that are in contradiction. So my ontology is inconsistent. And the reasoner just tells me that I'm doing something very bad here. So sometimes you want to use this for your own advantage. Sometimes it's an error. It depends on how you define your ontology and how you're using it. This is really, when you use ontologies, the only limit is your fantasy. You can design it to make use of the instance checking, to rely mostly on the consistency checking, or even you can use something called SWRL rules, which are here, which are they're not supported by all the reasoners, but the most important ones does. And there are some if this, then that rules, kind of. So in this case, we're going to do something like, if two robots, we have robot 1, robot 2, and they're in the same location, is in somewhere, then I want to trigger an event. So we can also have this kind of rules to enhance the reasoning capability. And by designing a system that makes use of these three aspects, let's say, we can get some pretty complex and interesting behaviors, okay? So why you should care about it? So ontologies in robotics have already been used. If you go through the state of the art, you'll find some very interesting projects, some of which I have referenced in the text here. The point is that you will see that it's quite complicated because the only API available for OWL is written in Java, which, as you know, it's not immediately supported by ROS. And this means that to integrate in ROS, there have been developed some workaround. And not only that, but since ontologies can be so different from each other, they're just databases, it depends what kind of techniques you're using. It means that it's not easy to define a general framework. So everyone was just building from scratch their own framework for their specific application. And we realized, we really tried to think how to get around this and make this more accessible to everyone. And we finally realized that you couldn't create a general framework for this, for sure, but you could create a suite of tools that makes writing some code to work with ontologies extremely easy and to be shared among all the nodes in your ROS architecture. So sort of a centralized repository of different database in an ontological form that you can access and that can communicate among each other. And this piece of code is Armor that I'm going to present you today, okay? So this is the first part. Now, I'm not going to go through the whole installation process because here you should have everything already installed. I'm just going to quickly present you what are the components, okay, and what they do. So ROS Java, I don't know if you heard about it, is an extension of ROS that initially developed to run Java applications in ROS for Android use. In this case, I mean, we use it for different scope, of course, for different goal. And yeah, you can install it from the official repositories now. This just allows you to run Java code in ROS, just like a regular node, okay? Then we have this Armor, which is sort of the core of Armor, because it's just a library that has been developed in our lab by my colleague, Luca Buoncompagni, that fundamentally abstracts the whole API. As I told you, all API are written in Java, and they're kind of low level and with some weird design patterns, so they're quite complicated to use. Doing also very easy operations like adding an individual or something to an ontology, it usually takes quite a few lines of code. While with this sort of library, everything is much easier, and it also allows you to manipulate multiple ontologies in a thread-safe way. This is important in robotics because, as we will see, you're usually going to work with multiple ontologies, okay? Then we have Armor, which I mostly told you about before, but we're going to see something more soon. And then, okay, the messages, and this Armor Python API, which it's going to be the main example I'm presenting you today, which is just a very simple Python library that you can include with some functions that fundamentally make service calls to Armor to modify this ontological database, right? And the last thing you can find online is this, and this is the address of the, the address of the repository I created with this README and the code especially made for this demo, okay? So if you want to come back at it later, you can just go here. So great, now I'm not going to build it because we already have it. I'm going to close Protégé, and we're going to get to the main tutorial, all right? Or at least start looking at something, because some parts of the demo I created are a bit slow, so we'll have some time to talk more while the demonstration runs, all right? So let's start with something easy. Now, there is a step that you need to take here. You have to come to the Armor folder and run this script here. Here it is. So this script here, it's supposed to be run only the first time after you build your workspace, but in this case, when you work on this sort of virtual machines, you have to do it every time you start a new instance in RDS, okay? So it's pretty fast. So this is just to make the use of ROS nodes a bit easier, because the syntax to launch a node or to run a road is a bit different and very verbose. Well, in this way, it becomes much more convenient, okay? So great. Let's try to run Armor. So Armor, as I said, is just a service that provides an interface to ontologies. You can load ontologies, you can query them, you can modify them, and that's it mostly. So here, let's source the workspace, or it won't work. Okay. Okay, great. Let's run this. So this is a script, and also open in the IDE, that fundamentally use this Armor Py API just to do a very quick test. You see, it's very fast, it's nothing complicated, but let's have a look at it together, okay? So if you come here, there is scripts, and the last one should be the client test. Exactly. Let's open this in a different window, so we have a bit more room here. Okay, great. So you see, what we do here is just initializing the client, which is done here, by the way, and doing some very simple operation, like add an individual to a class, doing some manipulations, and then reason, and finally save our inference. So whatever modification you do, they're not, let's say, they don't remain at the end of your work session. You have to save your ontology if you want to. And okay, let's have a look at Armor. What does this commands mean? I mean, if you open, for example, manipulation, you'll see that everything it does is just filling up the fields of a message, which is the Armor message. And if you want to look at the Armor message, you just come to the Armor documentation page. Here, what are the pros and cons of Armor are very well explained. And you will find in particular this part. So you see the message structure is very easy. You have a client name, which is the name of the client that is doing the operation. This is self-declared, so you can have more than one node actually declaring itself in the same way, so that if you have multiple nodes that works, let's say, on perception, you may want them to be named the same way. The reference name is the name you assign to that reference. That is the reference to an ontology. You can have more than one ontology, so each of them must have a different name. And then command and the two specs, they are what defines the operation that Armor should take, okay? And the arguments required for that operation. So if you come to comments documentation, you have a very long list of all the operations you can do. So this is just a subset of what you can do with all API or with Armor. But in Armor, this is, let's say that in robotics application, this is everything you need. Because in robotics application, you usually create in Protege your own database before in terms of classes and properties. Then you use these comments, especially manipulations, to add the data incoming from your perception, for example, or from some other part of your system. You reason, and then you pull the data you're interested in, okay? So, for example, when we before we were loading a new ontology, what is the command? What we were doing is just load file. We give the file path. The IRI is just something in your ontology that identifies it. You will see it in Protege, and which reasoner you want to use, and some flags that says if you want to use buffered manipulation or buffered reasoning, which simply means if you want modifications to be applied immediately as they're sent, or to buffer them and then manually apply them, and the same for reasoner if you want to reason after every modification or wait for you to manually send a reason request, okay? And all these things, anyway, can be changed later. There are some commands to change some of these settings. So this is just the initial configuration, let's say. So, okay, good. Let's go back here. We already seen Protege, so I'm going to skip this for a second. Let's keep working a bit from the terminal. So let's try some commands according to what we have just seen. And you see, I filled up already the message according to what I've just shown you. I click and I get a response. So was the response successful? Did it time out? What is the exit code? If there is an error description, is the ontology consistent right now? What are the objects I queried if I made a query? We can try a couple of more commands just for fun. For example, we can add an individual. This is just exactly the same as I was doing in code with the Python library. I can also run a reasoner. Okay, so this reason. And finally, I can also save if I want. Now, I'm not going to do it because I think I'm running a bit out of time, so I want to speed up things a bit. Anyway, great. So if you want to use the Armor Pi API, this is just an example we wrote. It's very easy. There are just some calls, these messages. You can write some. That was intended to be an example, okay? You can use it, of course. Not all the functions are included. We add them as they're needed. But this is mostly an example if you want to do the same in your code, or if you want to write the same in C++, let's say. And pay attention that here, maybe you see, where is it? Here. You see a lot of code, but most of this code is just caching exception and stuff. In the end, what does the magic is just that string, okay? So very, very easy. Good. So now let's start the simulation, the real simulation. You have to launch this file here, turtlebot house, okay? I just got this file because I wanted a nice, let's say, smart house environment to work with. Because let's say that smart houses is kind of a popular application for this kind of things. So what are we going to do? We will have two robots, and these two robots will run together. Each of them will have his own knowledge base, ontological knowledge base that represents its belief system. And then there is going to be a third database that represents the home. So we will send comments in a semantic way by updating the belief system on the robot, saying that the robot should be going somewhere. And the house will check on the two smaller ontologies and say, okay, when they're in the same room, this triggers an event that I should take care. So in the smaller ones, we don't really have a lot of reasoning. In the second one, we have some reasoning. And the important thing is that not all the data is duplicated. Maybe the small ontologies have a lot of knowledge about local things that the robot should care about, while the house, maybe it's not interested in the small details, but has knowledge of all the robot's position because it has to take care of their coordination, right? Okay. So let's see. Semantic. Okay. Now this is running. No. Okay. I will need another. Oh, I can kill this. Okay. And let's do like this. This. Right. And this one. Okay. So this will launch the tutorial. And now, this one. So if you open this simulation here, you should see two robots popping up. Okay, here they are. There are two turtle boats. So the rooms are like this. This is bedroom 1, bathroom 1, living room, bedroom 2, kitchen, and bedroom 2. Okay. Great. So let's send a comment. So you see, I'm just going to add this to the knowledge base of the robot. And this should start. You see, it's already moving. So this semantic command was translated into move base command, and now the robot is moving here. Maybe I can make this a bit bigger. Maximize. Okay. I can do the same for the second robot by taking this, and let's try to push them in the same room. Okay. In the meanwhile, I can quickly query, for example, where a robot is going to. This is also displayed here for convenience, but let's do it the Armor way. So where is it going to? It's going to bedroom. So this error is just some error that sometimes happens in simulation due to synchronization. The call was successful, so don't worry. If you see success through, it's good. Okay, great. Let's see, I wanted to show you quickly the code for this. So if you come to Armor RDS tutorial and you come to the scripts, you see that control, okay? So the control is the node that controls each of the robots. It's just duplicated. It moves, it goes, and let's say that in the loop it does two things. It checks where the robot is, and it checks where the robot is going to. And if the value that is in the ontologies, it's different from, let's say, if the value that we see is different from the previous value that was there, then we trigger a move-based action, and we just start moving. Okay, so it's kind of reactive. Now we just update the belief system, and it starts doing something for us. Where is the graphical tools? Okay, so you see the robot, it's moving much faster than it was doing yesterday. So what do I expect is, you see the robot is already here. Now, the house ontology will check, as knowledge of both robots, it will check when they are in the same place. And if they are, it will say, well, no, this is not a situation I like. So I will move the second robot, which has lower priority, to another room, which is the living room, just because it's very big, so the chance of collision is not that high. Okay, you see, now it changed, and it will just turn back. Why this? So let's quickly have also a look at the code of the HouseMonitor. What does the HouseMonitor? What the HouseMonitor does is it checks for some triggered events. So we have a class triggered events, and we have that rule I showed you before that says that if you have two robots in the same room, then you have to put one there is an individual that represents an event that should be moved to the class triggered. So I can query the class triggered, and if there is more than 0 triggered events, do something. So you see, this scales very well because I can have different triggers with different events, with different names. And then in the code, I can add events handlers, for example, just to this. And this is much better than having a lot of if, else, switch cases, because all of the logic is managed in a comprehensive way by the ontology instead of by me. Okay, so my code is actually quite short, right? It wouldn't be much longer if I had like 10 rules or 20 rules, right? Good, so I think we are very close now. The simulation is over. I want to, okay, just another thing, you may have seen somewhere in my code, data properties. They're just like regular properties, but instead of linking two objects, they link an object to a value like a boolean, an integer, and so on. All of the most important are supported in Armor, so no problems. That's it. That's it. I just want to leave you with some tips and remarks. Okay, so I think this should be clear by now, but it was just implicitly stated, so I want to make it explicit. So in robotics, we usually prototype an ontology offline just to get the structure, but the important thing is iterate. So you create your ontology, you check that it works by connecting to the rest of your framework, and then you go back and so on and so on. But the ontology is always made offline. You usually just populate query on online. Okay. Also, Armor, as I said, implements everything you need for this kind of use. And what's nice is that you don't need anymore to know Java to use this, because most of the people in the robotics community, they're mostly skilled in C++ or Python, and now you can just write your node in one of these languages and do service calls instead of learning Python like I did during my master thesis. Okay. And then this is really the most important remark. Keep it fast. So if you look at the ontology world, it's mostly computer science people that works with huge database, but this is not your use case. So you need some tricks to keep it fast. So the first trick is split your ontology. Like many algorithms in AI, this goes towards numerical combinatorial explosion. So having several smaller ontologies is always faster than having a big one that is equivalent, okay? Another thing is use buffered reasoning whenever possible. So reasoners are not all the same. So buffered reasoning means, as I told you before, that you don't reason after every action, but you do it only when requested. So try to do a lot of modifications and then manually send buffered reasoning command, which I mean to reason. Because in this way, you know exactly when you're going to reason. And this is important because reasoning is usually the longest action, and it's kind of blocking. So you cannot make queries or anything else while you are reasoning. And then if that's it, if you can choose, pick a reasoner that is incremental. Incremental means that every time you reason, it doesn't re-reason everything, but it just modify a little bit what you reasoned before, so it's faster. And the last thing I can advise you, it's avoid inconsistencies and re-reasoning as an even trigger action reasoning loop. So I know this is kind of confusing, but what I mean is a lot of people use inconsistencies as a way to detect specific events. But I wouldn't really advise this in robotics application because it involves re-reasoning a lot of times, and it's not very clear what is going inside. So this is very good from a logical point of view, but as a developer, I don't feel this is the cleanest solution. So I would invite you rather to control very tightly the logic of your ontology, know exactly what happens, and go and poll specific classes, individuals, or properties of, say, the individuals. Okay? So thank you. I'm done. I hope this was interesting to you and that maybe some of you will consider using this kind of technologies in their future projects. And if you have any question, please, I'm here to answer them.
Okay, so thank you very much, Alessio. So an applause.
Thank you.
Very good. So you can unshare your screen now, so we can see your marvelous face.
Yes. Can you see me? Great.
Yeah.
Yeah. Okay. So now we're going to do the Q&A. If there are any questions, please post it in the Gitter so that Alessio can crush them. And yeah, so let's see what we have there.
Okay. Should I look for the questions on the Gitter, or you're going to relay them to me?
We are both, I suppose, the fastest way.
I don't see the Gitter anymore. Sorry. I think
Word go the question.
We are going to relay them.
Okay, thank you.
So let's have a second. Okay, we have one. Let me have a look. Okay. The question is there any set of ontologies? Can we download already created ontologies from?
So yeah, sure. If you look at the README left inside, there is the link to this tutorial, and there are the one I created for this tutorial as an example. But inside of the README, there is also a link to a very popular tutorial called Pizza Ontology. You can have a look to understand. If you're referring to ontologies about robots, I wouldn't say so. I mean, you can look in the state of the art, and maybe I can just link you some examples. But yeah, just remember that they're very application specific. So they're not going to apply for sure to your use case. You will have most probably to write one for yourself. Okay?
Okay, great. I have another question.
Yes.
So this question is, are there any APIs apart from the Python one? So
okay, so no. The point is that the stack is like this. There is all API, there is Armor, and then there is Armor. And you're interfacing through messages to Armor. The API, the Python API we wrote is just a set of commands that make calls to Armor. And at the moment, we only have that. So if you want to work in C++, you have to write something similar, but you'll see it's just filling up a message. It's very easy. If you want to do something more complex than what we have done here today, I would suggest you to work with Armor instead, which is the core of Armor. It has much more capabilities, and it allows you to get really deep inside the ontology, but then you have to work in Java, okay? And it has nothing, I mean, Armor is not ROS dependent. You can use it in any Java project anyway, okay? We already provide a ROS version, like a ROS library, but you can use it anywhere you want, okay?
Okay.
Okay, so let me check if there is one last question, and if not, we're going to leave it here. No, it doesn't seem like, so I think we'll leave it for Alessio here. Thank you very much, Alessio.
Oh, thank you.